So in this video, we're going to look at formal charge. And formal charge is essentially a hypothetical charge on an atom within a molecule, and it's used to predict the molecular structure when you have multiple options of the ways that the atoms can be built together. So how do you actually calculate formal charge? Well, formal charge is calculated using this formula that you see here. And the formal charge is calculated by taking the number of valence electrons that an atom has available and subtracting the number of lone pair electrons on that atom in the Lewis structure and subtracting half of the bonding pair electrons within that structure. So if I were to calculate the formal charge for nitrogen in this molecule, NCl3, that the Lewis dot structure is already shown here, what I would do is I would put the formal charge is equal to 5. So 5 is the number of valence electrons that nitrogen normally has available. And then I'm going to subtract the number of lone pair electrons attached to nitrogen, and it turns out that there are 2 lone pair electrons, so I'm going to subtract 2. And then I'm going to subtract half of the number of bonding pairs electrons. So there's 2, 4, 6 bonding pair electrons. I'm going to cut that in half, so I'm going to subtract 3. And so the formal charge for nitrogen in this atom is 0. And so that is how you calculate the formal charge. Now, if I were to do that for the atom chlorine, right here, the one on the right-hand side, I would go about that process the same way. So the formal charge is calculated as the number of valence being 7. I'm going to subtract the number of lone pair electrons, and it turns out there's a total of 2, 4, 6 lone pair electrons. And then I'm going to subtract half of the number of bonding pair electrons. And so there's 2 bonding pair electrons attached to chlorine. I'm going to cut that in half, and it's going to be 1, and that's going to give you a value of 0. And if you go through and calculate the formal charge for the other 2 fluorines, and when you're calculating formal charge, you must do the calculation for each individual atom, even if it's the same type of element, because they could have various different formal charges. You would calculate these, however, to be 0. And there are some guidelines that when we're using formal charge in order to discern whether or not we have the correct drawing of a structure, that one of those guidelines that I'll go over here in just a minute is the fact that the most optimum structure for a molecule is to have all of its atoms sum up to a 0 for their formal charge. And this is if they're a neutral molecule. So what are those guidelines that I was talking about? Well, it turns out that the guidelines for when you're drawing a structure are pretty useful, but also you get used to using these guidelines as you're practicing using formal charge to predict a molecule structure. And so I've kind of taken and tried to put the guidelines that were written in your textbook in a way that makes them a little bit easier to follow. And so essentially what we're going to say is that a molecular structure with a formal charge of 0 needs to have some of the following kind of ideas behind that. Preferably, and you can probably rank these actually from the top to bottom, the top being the most preferable way that formal charges could be utilized to predict a structure, is that all over you have a formal charge of 0. And then if you happen to have a structure that has some non-zero formal charges, you want to try to have those with the smallest number of non-zeros. And I might even go a little further than that to say that if you had a combination of -1 and +1, or you had -2 and +2 as two formal charges within a structure, you might even want to use the formal charges that are closer to 0 rather than not. And so that might be something I might add to these guidelines. The other thing is that we try to utilize locations of charges as well. So if you have two atoms that are adjacent to one another that have zeros, that's probably indicative of a good structure. Also, if you have charges like, say, like I had that -1 and +1 here, if they're opposite of one another, they need to be adjacent to one another. And those things tend to kind of predict that that structure is a good structure. And the other thing is that, say, for instance, you just have no combinations of structures that have zeros, they're all non-zeros, and you're just it's very difficult for you to kind of discern or use any of these guidelines. This last one would be your last resort. And this one's saying that if you have a formal charge that's negative, put that on your most electronegative atom. Your most electronegative atom. And again, we're pulling back in that electronegativity periodic trend. So go back and look at that particular figure so that you can have those values as a guide. So let's practice using formal charge for a substance. And the substance we're going to do this of is thiocyanate ion. And this thiocyanate ion has 1 carbon, 1 nitrogen, and 1 sulfur, and has an overall charge of -1. So if I said that it just had those particular atoms together in its charge, you may not know what is the appropriate combination or attachment of those atoms to one another. And you might imagine that you could potentially put the structure together where nitrogen's in the center, or the structure together where carbon is in the center, or the structure together where sulfur is in the center. So how do you know which one of these is the correct thing? So I went ahead and I used the NASA table and calculated that there should be 4 bonding pairs and 4 lone pairs. And then using those values, I built 3 different structures, which the NASA table works with all 3. So you're again going, I don't know which structure is the appropriate one. So this is what we're going to do. We're going to calculate the formal charge for each one of these atoms. And from that formal charge in each structure, we're going to try to calculate or predict which one might be the most appropriate one. So again, remember it's valence number of electrons minus lone pairs minus half the bonding pairs. So for this carbon over here, we're going to start with this structure. We're going to start with the atom to the furthest to the left. So carbon is a valence of 4 minus 4, because that's the number of lone pairs, minus 2, and that's the half the number of bonding pair electrons, which was 4 total. You have 2 here, 4 total, half that's 2. So it's going to give you a value of -2. So now nitrogen is 5, that's its valence, minus 0, there's no lone pairs on nitrogen, and then minus 2, that's the, let's see, there's 2, 4, 6, 8. I'm sorry, that should be minus 4 here. So that's going to give you a +1. All right, let's do the next one. So sulfur is number 6 valence, minus 4 lone pair electrons, and then minus 2 for its half of bonding pairs. That's going to give you a 0. Okay, so now let's go to the next structure. So nitrogen, 5 minus 4 minus 2, that's going to be a -1. Carbon is 4 minus 0 minus 4, which is 0. And then sulfur will be 6 minus 4 minus 2, which is 0. That's looking better. This structure, based on the fact that there are 2 zeros versus 1 0 in the first one, we could probably cut that first structure out and say more likely than not that this is the structure, but then we need to compare it to this one. So let's see what it says. So let's do carbon. That's 4 minus 4 minus 2, so that's negative 2. Sulfur is 6 minus 0 minus 4, which is plus 2. And then nitrogen is 5 minus 4 minus 2, which then ends up being, what, minus 1. All right, well, that structure is even worse. So that has no zeros whatsoever. So we can pretty much essentially say no to this, no, and no. This is most likely the structure for thiocyanate ion, and we can use our formal charges to discern that or to predict that. So this has been a video on formal charge. Look for our next video on resonance. I'll see you there.